All right, hello everyone. So you've done some regression. You're becoming more adept with interpreting what regression has to tell us. I want to add something into the toolkit. I want to talk today about interactions. And I want to start. I'm gonna actually do an interaction here and see if we can interpret what it's telling us. But I want to start with a little bit of description to try to help set the stage for what we're talking about when we talk about interactions. When do I need an interaction? Well, there's a. I think the answer to that starts with what is an interaction actually. This is my definition. I don't know if it's a textbook definition. It's a conditional effect. A conditional effect. It's when X affects Y differently depending on the value of some other variable, which we'll call Z. So that's saying again that our independent variable X is influencing Y differently depending on the value of Z. A conditional effect. I'm going to just make sure that definitionally sinks in. That's a really important conceptual insight that I want you to carry away. If an interaction is the mechanical tool that we use to understand the nature of that conditional relationship, to understand the interactive effect of X and Z on Y, how X affects Y when Z is one value, and how it affects Y differently when Z takes a completely different value. An interaction is the methodological tool we use to understand the nature of that effect. That's important. Okay, so you need one when there is a situation in which X is affecting Y differently depending on Z. Well, you say, that's useful, Paul. How do I know when that's the case? Well, there are a few ways you can approach this. This is all about people analytics, and generally when we're talking about people analytics, we're talking about big data sets. And one approach would be I can just start creating interactions, and I'll show you mechanically how to do that and seeing what happens. And okay, you could, although I'm going to encourage you not to do that. I think I want us to be purposeful and disciplined in trying to keep our analyses tethered to some sort of theory. Try to keep our analyses tethered to some sort of theory. Furthermore, some data sets are so big that it's not possible to, or be very, very time consuming to try a bunch of different interactions. So I want to suggest that we test for an interaction. We have a theoretical reason to believe that the nature of the effect on Y is conditional on Z. So where does that theoretical reason to believe come from? Well, it can come from a few different places. And I'm going to conceptually demonstrate one way it can come. I'm going to show you in just a moment in Jamovi another way it can come. But I'll tell you sort of a practice story. An in-practice story. Imagine an experiment. We have a theory that unexpected breaks yield increases in productivity for tomato harvesters, people working in fields harvesting tomatoes, and unexpected breaks will yield improved productivity. So we run this experiment. We've got a control condition, and we've got an experimental condition. In the experimental condition, these harvesting teams are being surprised by these unexpected breaks that are occurring. We don't really need to get into the weeds. By the way, if you're interested in this, we actually did run this study, recently published a paper. We find that in the control condition over the period of our experiment, average productivity is 24.5 tons per hour. In the experimental condition, average productivity over that same time period is 25.2 tons per hour. So it is higher, but it's not statistically significant. It's not statistically significant. I'm the sort of person, and I encourage my students to be this sort of people that, in trying to understand the phenomenon, to try to understand it through the lens of descriptive data. That is, don't start by running a bunch of regressions and trying to see what's statistically significant. Try to develop a conceptual understanding of the phenomenon by looking at descriptive data. Imagine, so one reason why it would be the case that this wouldn't be a statistically significant relationship is, again, we've got 24.5, that's the average for our control condition. We have 25.2, that's the average for our experimental condition. One reason why it might not be statistically significant is that those populations overlap an awful lot. Paul, it turns out that your theory, your operating theory, that unexpected breaks yield productivity increases was wrong. There is no systematic productivity increase. If there was, our data would look like this. These two populations wouldn't be overlapping very much at all. So we could look at the underlying data, and if we see this form of data, we would have a sense that your experiment just doesn't work. It doesn't yield what you think it would. But imagine that we look at those data, we look at those underlying distributions, we see something that looks like this. That is, we see the control group has this normally distributed population of productivity, but the experimental group has this bimodal distribution. That is, we have a whole bunch of individuals that are way up here, and we have a whole bunch of individuals that are way down there. This suggests that the experiment had divergent effects, that for some people it worked really, really well, and for some people it backfired. When I see a bimodal distribution like that, that's a signal that there's a variable that accounts for that bimodality. There's a variable that accounts for that variance, that very, very wide variance. And I want to figure out what that is. And that to me is a cue to start to think about, why would unexpected breaks affect some people positively and other people negatively? Well, this is where theory, this is the seed for theory. It's giving us sort of a targeted question to ask. I hope that makes sense. One theory that emerges intuitively is perhaps there's something about individuals' personality. People who like control and structure and rigidity, like conscientiousness, people who are high in conscientiousness. Perhaps unexpected breaks backfire for them because it feels like this is something that's random and haphazard and out of their control, and it causes a lot of anxiety and stress. Whereas for people who are not high in conscientiousness, this provides an unexpected opportunity to just breathe and pause and rest, and the relaxation benefit manifests in productivity after the fact. That would be a candidate moderator. That would be a candidate variable for that Z in our conditional model that I described on the prior slide. That's one way that you can cultivate a theory. It starts with trying to understand the nature of the underlying data. In this case, we see bimodality or wide variance for that one group. And now we have a sort of targeted search. What variable might account for that wide variance or for that bimodal distribution? Sometimes the theory comes to us more naturally, though. I posted a data set that you can use and follow along. I got this from Kaggle. Kaggle? Yeah, I got this from Kaggle. It's an online repository where people post data sets of all sorts. And I just downloaded this. It's a data set called heart disease. And it's data from individuals who were tested at a hospital for heart disease. And heart disease in this particular data set takes a range from 0 to 4, where 0 is there's no evidence of heart disease, and 4 is the most extreme level of heart disease, and then 1, 2, or 3 or varies in between. That's going to be our dependent variable. What we're really trying to come up with is a model that predicts the incidence and severity of heart disease. Incidence and severity of heart disease. And now, if I were to just ask you, based on what you know and understand of the world, you could probably come up with a handful of candidates for variables that might predict the incidence of heart disease. I'm going to toss out a few of them. I have this general and emergent sense that biological sex probably matters. That is, actually, my intuition is that people who are males have a higher incidence of heart disease, and that the heart disease is more severe. So I think that matters, and I'm going to toss that in as a covariate here. We can choose covariate or factor here. At the moment, we're just going to leave it as a covariate because it is it's only one or the other. And I also think age matters. So we're going to toss it in as well. And then finally, I think that, and if we look at the model, it turns out it does. And finally, I think resting blood pressure probably is a reflection of something that is predictive of heart disease. So the measure we're going to toss in here is a measure of a blood pressure measure for at the time people were admitted to the hospital. So we're going to toss that in. And yes, it looks like that's associated with heart disease as well, although barely from a statistical significance standpoint. But perhaps you say, well, actually, I think blood pressure levels sort of systematically, the effect of blood pressure on heart disease. I have this theory that that blood pressure influences heart disease differently for males relative to females. Now, we could come up with that theory based on, reading or talking with medical professionals, or by actually looking at the underlying data. I'm not going to do that here for the sake of time, but we could look at the underlying data, and we might see that, for males and females, the relationship between heart disease and blood pressure look different graphically, something analogous to the graphs I just showed you. So I'm going to walk through mechanically how to do this, and we'll see if we can sort of make sense of what it's trying to tell us. Jamovi gives us a kind of cool tool that we can use to test this, to create an interaction. I'll show you two ways you can do it. Our theory is that that the effect of blood pressure, X, on Y, heart disease, is conditional on some other variable, Z, which we're going to say is sex. Mechanically, the way you create an interaction in your model is you just multiply those two covariates by each other. It turns out that Jamovi gives us a really easy tool that we can use. Sex is what we want. That we can use. We select here under model builders those two predictors, select interaction here, and it creates this multiplied value for us. And it drops it into our model. So now let's see what our model has. Our model has the intercept. Remember, a linear regression takes the form y equals mx plus b. This is b, the intercept. And these are the various mx's. First we have sex. There's a value associated with male. 1 in this case is male, 0 is female. There's a value for age. So for every additional year of age, the increase in your heart disease, we would predict the increase in your heart disease range to be 0.02. There's an effect associated with blood pressure, resting blood pressure of 0.0186. That means for every additional point in blood pressure, we would expect heart disease severity to go up by 0.0186. And then finally, we have this interactive effect. The mechanical interpretation here is that the multiplied value of blood pressure times sex is negative 0.0174. So we can look at that, and the p-value is less than 0.05, it's 0.025. We can look at that and we can say there's a significant interactive effect here. And we can say that we now know something about the differential effect of resting blood pressure on heart disease for men relative to women. And we know that it's significant. But I think it's really important that we try to understand what this means in practice. In order to do that, I think it's useful to sometimes model what the predictive values would be for at varying levels of the covariates here. So I went and actually did that. I created an Excel spreadsheet here. I took the coefficients from our regression here. I put them in this Excel spreadsheet. I hope you can see this. Our intercept is negative 3.5554. The coefficient on resting blood pressure is 0.0186. Coefficient on sex is 2.9658. Coefficient on age is 0.029. And the coefficient on our interaction is negative 0.0174. And then I just created a matrix here that gives us predicted heart disease severity values at varying levels of resting blood pressure for females and for males. At the moment, I'm just assuming that we're running this for people who are age 60, but our regression is such that we would expect slightly different outcomes for people who are 61 relative to people who are 65, relative to people who are 70. And in just a moment, I'll show you this, but let's see what this is telling us. First of all, our model suggests that males, the coefficient of 2.9658 on male, suggests that males on average have more severe heart disease on average. But the interaction is telling us something else interesting. It's saying that, if we look at this, it's saying that for a female with blood pressure at 94, our expected heart disease severity is negative 0.067. Now, it's worth noting that that value never actually appears in the data. The lowest value you can have is 0. But really what this is, that's because this is a linear model. And the linear models, particularly on those margins, can yield values that are beyond the bounds of what occurs in practice. But what this is really saying is for females with blood pressure at 94, which is the low boundary of the blood pressure observations in our data, we would expect no incidence of heart disease. For somebody at 100, we'd expect something very, very close to 0 as well. For someone with 110, it's 0.23, still pretty close to 0. We're still sort of living in that realm where there's not really much heart disease emerging. 132, again, still not much happening there. But then we get up to 150, and now we're at that point where we have sort of low-level heart disease. And then it goes up pretty rapidly from there. It goes from 1 to 1.3 to 1.5 to 1.9, and if we got higher, it would presumably get much higher. Now let's look at the same pattern for people who are male. Well, 94 we're already at 1.263. Sorry, at blood pressure levels of 94, we're already at 1.263. We're already at that point where, for a male, we would expect low-level incidence of heart disease. 100, it goes to 1.27. At 110, it goes to 1.28. 132, it goes to 1.31. The implication of this particular model, predicting heart disease severity, is that systematically, men are more likely to have the occurrence of heart disease, but as blood pressure goes up, blood pressure has less of a profound effect on the severity of heart disease for men relative to women. That's what this coefficient of negative 0.0174 is telling us. It's saying that for people who are one on sex, who are male, the effect of blood pressure is not nearly as severe as it is for females who are in this box, the 0.0186. And if we just look at that, what this sort of telling us is that for males, increasing blood pressure has almost no net effect on severity of heart disease. I'm going to share these data with you. You can try to replicate this. But the way I want you to think about a conditional effect is that there is a relationship between one variable x and another variable y. There's a relationship between blood pressure, x, and heart disease, y, that is positive and significant, but that the nature of that relationship differs as a function of some other variable, y, which is sex. And what this interaction is telling us is that for people who are male, the relationship of blood pressure on heart disease is reduced. It's buffered by being male. And we can see that show up here that as blood pressure goes up, the severity of heart disease it still goes up for men, but not nearly at the same rate as it goes up for women. I don't know what to make of this in practice. It's intriguing. It's obviously based on a relatively small sample of data, and I'm sure there are lots of other covariates that go into this, but I hope that this has helped you understand how to interpret interactions. I do want to show you very quickly one other way that you can create an interaction. Here we allowed Jamovi to create it for us, but we could actually create that that variable and store it in the data. We can create a computed variable. We'll append it here. And our computed variable we're going to call sex times, what's our variable name? trest bps. And the formula is going to be sex times trest bps. And now we have a formula in here that is the multiplied value of sex, which takes a value of 0 or 1, and trest bps, which takes a range from 94 to 200 or something like that in our data. Now we can go back to our analysis, our regression, and we can just add that calculated variable into our model, and it comes out with the same exact estimate. So what we did here is we manually created that variable rather than allowing Jamovi to create it on the fly on our behalf using the model builder here. I hope you find this whole thing useful and informative. Thank you for watching.